So this will be our asynchronous material. And so this is with a little bit with class 3. This will also get over into class 4 a little bit. So just to remind you, today I am working with you on project 1 consultations. Oops. So that's what I would be doing. Undoubtedly in your project, right, you'll end up hopefully with there would be like a major space, a large open space. And so in that, you'll end up having to deal with large or sort of atypical spans. And so that gets us into a really different category. And so we'll talk about that. It's dealt with in the handbook. And so we will get into dealing successfully with long spanned structures. And so in your building, most likely you'll end up with some sort of a truss that should be in there. So, with that project 1, right, that we're consulting today, so you should have some spans, you should have some dimensions, your grids, right, and really your layouts. And so by doing that, we'll get some preliminary sizing, which will allow us to understand, really the main thing is dealing with depth, required depth, and therefore story height, right, as a requirement of the structure. So by getting these large spans, that gets very quick implications on what material we can use. Right? And we would say that that would be in a typical fashion. So sawn lumber, I-beams, and the member selection, right? And that's where we get into some atypicals, right? A little bit of trusses, and just how we end up. And those trusses can be made of any material. And so we'll talk about that a little bit today as well. So you have a lot of examples in somewhere in your project 1, right, where you will definitely have something that would be a short span floor system. So your typical post and beam, right? Beam, girder, sort of joist combination, or there could be a slab involved, either with steel or with concrete. So we've got, and these spans would really typically, we'll go over them in just a minute, but we're talking about really less than 30 feet. And then once we get beyond that, and again, it depends on material, but really, once we get sort of 60 feet, once we get definitely beyond 60 feet, so we end up then having to use some sort of a truss system, right? You may have an arch where you may have a vaulted structure. Could have a dome structure, more in bridges, but you could have a cable structure. So that probably wouldn't be in terms of what you've got, but the idea of the arch and the shape of the arch will become very, very important, and the trusses that we'll end up designing as well. So what we end up getting into is not only both strength design, but also depth requirements. So that depth requirement comes from not only stress analysis, but also from deflection. And so, like for instance, for sawn lumber, which would be a section that would be full sectioned right there. So this would be your typical sawn lumber. Don't know why that keeps coming up. I will try and not have that happen. And so this is on page 18 in your handbook. But those spans generally are going to be less than 20 feet. So not only does self-weight become an issue, so for wood, from a deflection point of view, it also involves Young's modulus, which deals with the stress-strain relationship. So um, wood is generally a soft material as opposed to steel. Now we can do some stuff for longer spans. With wood, we can make glue lamps, which would be in profile, would be many. This should all be the same, but these would be glued together. And so the only issue with that is, the money. But for that money, for what you get, if you're just using wood on the project, then you're able to span, something like 40 to 60 feet would be typical for a glue lamp. And of course, the other thing with a large glue lamp or anything that's 40 to 60 feet long is it has to be moved. It has to be transported to the site. And so that also would be something that hits with in the money department, transportation. So typical concrete, and so when I say typical concrete, I would mean solid beams. Pen is acting up today. So something that looks like that, you'd obviously have some rebar top and bottom in the tension zone. And so concrete, you get a little bit longer span, you get about 30 feet. Generally, this is going to be built on site, but you're dealing with moment of inertia issues because you end up with what's called a cracked section. So that's why that reinforcement is down in the tension zone, and the concrete itself can't be in tension at all. And really, from a practical point of view, this one really becomes true that with concrete, the weight becomes a strong issue. However, from a finish point of view, you can use that material, concrete, as exposed material. So that's one of the upsides of it from a cost point of view. But you do pay for it in terms of weight. And as we talked about last time, that becomes mass, which becomes a seismic issue. So just to keep that in mind, that would be why you would see things called pre-stressed concrete, pre-stressed concrete, post-tension concrete. Those are very challenging. Those are sort of higher level, if you will, from a construction point of view, for sure. The other thing that slab, so we kind of had that on, you're working on that with homework. On the homework, we just analyzed that beam right there as a single beam. But the fact is that you can use the slab as part of a T-section analysis. So that's how you can get a little bit of longer spans with concrete, especially when you use the slab action. And that same thing is done with steel. When you have a slab, perhaps a concrete slab on top, it just becomes the connection from the steel beams to the concrete decking that would be above. So typical steel, and when we say typical steel, I would just mean like a typical I-beam. So you've got some sizing in there. That's what you would have done. Also working on that with homework. And so typically you're dealing with something, about 50 feet or less. It can be longer, but then it just depends on the loading, how it's framed in. So then the loads become a big issue. Both dealing with stress and deflection become both parts of it. As soon as that span, really goes over 50, 60, I mean, it's not a hard and fast number, But that's what that OWSJ, that really gets us into something that's quasi truss-like. And so those spans can be up to about 120 feet. And so that gets us moving in the direction of trusses here. Now those trusses can be, they can be constructed of all different types of material. So you would see in the bookstore at Cal Poly, next time you're in there, hopefully that's soon, that we'll all be back there, you would see some concrete trusses, steel trusses, you see those in the rec center. Steel sections could be circular sections, could be square sections. Wood, probably if you go out into your garage, you would probably see, or in the attic, you would see some sort of a wood truss structure. And so as we talk through this, you're trying to accomplish the same thing. What you're trying to do is get across a large span for the material that you've got. Here would be an example of several different types of trusses. Now these could be simply supported trusses, or they could be cantilevered trusses. So for instance here we could have a support here and a support there. That would be a simply supported. You could also have something where you had a support here and then maybe a support in the middle. So you would have a cantilevered section of it. So this really works in both of these possibilities, both simply and cantilevered. And the general issues with all of these are very similar. So if we were going to do just a solid beam design, so this would not be a truss right here, but just a beam with some sort of a span to it. And then you've got some combination of loads. So this is just homework 1. So on the top, you would have the material in compression. On the bottom, you would have the material in tension. And then here, this depth, right, that we keep talking about so much, and those minimum requirements, what that's doing is it is creating a couple. So the compression zone and the tension zone are separated by some distance. That distance is related very closely to the depth of this solid member right here. So the same thing is going to be true on a truss. We're going to have compression on the top, tension on the bottom. That would be for something that's simply supported. A little different with a cantilever, and we also have different span to depth requirements for it. But that's what we'll end up dealing with are the chords. So that gets into the moment capacity. So if we look at this truss here, we'll go for just describing what's here. You've got a span, right? That truss span. This would be simply supported. Bottom chord, top chord, or upper chord. We've got some overall span, and then we've got a panel length. So that span is broken up into pieces. And that length, we're going to be able to calculate it. Also, the depth is going to be a requirement. And, with these long spans, you're going to end up something that's going to need some decent depth to it. So you're certainly not going to have something that's too shallow. And so this is what's going on here is that we just kind of take a cut. So this is what's going on here is I've cut this thing. I've cut it. And so I'm representing that right here for you. And so on the top chord, you've got compression. On the bottom chord, you've got tension. They're separated by a distance d, and the moment capacity is going to be calculated by that force F. This has to be equal and opposite by equilibrium. So it's going to be F times D is going to give you the moment capacity. So there's a couple ways to make your truss, right, have greater moment capacity. Either increase the depth, right, or increase the capacity of the top and bottom chord. So increase F. So that's why those chords, right, are going to be designed, the one in compression is going to be designed much like a column. So you'll see that in the handbook. We'll get to the same section that we've got with column design. And one of the other things we would like to have from a, well, how far is the panel? We'd like to have about a 1-to-1 slope. That would be optimal. It's not always going to end up being that way. If you've got something where it's shallow, so the slope is, right, very short, right, or shallow, then you obviously put more on the forces to be able to grab enough moment capacity up there. If you have something that is very steep, then from a bay point of view, and so here we would be maxing out D, but then you also get into buckling of these members due to their length. So that's how we end up with optimally, it's not always going to be that way, but optimally we'd love to have about a 1-to-1 ratio on that. So we'll finish this thing up with a couple of pictures here. So this would be something like you might see in, right, typical wood frame construction. So this would be something perhaps in your garage or in the attic. So this is a bunch of wood. And so, here we're dealing with a pitched roof. So you don't have, something that's flat. This would be more for a floor that you would use, something that would be flat. Something that would be pitched would be used in the roof section. So you've got some spacing, right? These members are actually just normal 2x4s, maybe 2x6s. So this is just a way to, sort of a built up truss. Don't know why my pen is doing that today. All right, this would be, like I said, more for flat or for wood. So here you see the diagonals are not at 1-to-1. All right, they're a little bit flatter. So you put a little more stress on the chords. Take a look here at steel. So this would be a bridge. So the same concept here, you'd have the top chord would be in compression. Bottom chord down there would be in tension. Right, as the loads, now those loads could become from cars, also just from the self-weight. But here you get a little bit better look at something it's about 45 degrees right there. So you kind of see that coming as an optimal angle if you can create it. Here would be something out of concrete. Again, decent depth here, very decent depth here. When you're dealing with a bridge, you don't have, except if you need clearance below, but you don't have as much sort of restraint on the depth requirements. Here we've got a concrete truss, so it's a little bit of a combination. This is what you would see in the bookstore. Varandel truss, here would just be your diagonal members that would be showing up, and if you notice, those are about at 45 degrees. So you get a sense of the span to depth ratio. And again, it has to do also with what's framing into it, what also it's being sort of asked to do. So you see the big space down here that is available, and things can span and sit on that as well, framing out. So then just right on I'm going to do a couple of examples here, but on your project 1, right, you'd end up with something that would either be wood, steel, concrete, and probably going to be a little bit in the truss family. Most likely you'd end up with something, a major space, and that major space to have large openings for everyone to gather or to do something that could be in a lower floor. And so you end up with a height. So that's what we'll be checking, making sure you've accounted for the required depth, whether or not that's the actual depth, but you've got a story height that you have adhered to based on your span. All right, so we'll get to some examples of trusses here and go ahead and use examples of them as beams and girders, right, which would be up here. This would be a picture of something that is simply supported, so just determinate and supported at the ends. So there would just be the simple span right there. So the span to depth ratio, this would be from your design guide, would be somewhere between 10 to 12 would be an acceptable number. Make sure you remember units, right? Make sure you know that the span generally is in feet. So you would be getting a depth that would be in feet if you didn't know otherwise. Again, this is for very long span. Something that is very long. Going to have pen problems. So just remember that this long span up here, this would be something that would be 60 to 100 feet. So that's why we end up with pretty good units or a pretty good depth requirement. So we'll see an example of this in just a second. A cantilever, right? And so we would have a support that would not be at the ends. So this would be what's called the back span. Over here, we would have the cantilever. So this would be the back span. This cantilever, there's a little bit with ratio of what we call the backspan back here to the cantilever. So generally we want something that's about 2 to 1 is optimal from a design point of view. From what we call the span, that would be the overhang. I don't know why my pen is having such trouble, but there we go. There's a little bit better. There's the overhang issue, the overhang span. So that would be the length of that overhang right there. So also then back from the design handbook, we would have for joists, which would be more tightly spaced, the S over D, the span to depth ratio would be somewhere between 18 to 24. Again, trying to keep the diagonals optimal would be at 45 degrees if we could do that. So we'll go ahead and look at a theater roof truss here. So we've got a truss that's going to be spanning, right, 100 feet. We've got then some joists or beams that would be running in the other direction. So that'll be 34 feet. So let's go ahead and take a look at, given to us, we've got a dead load of 100 pounds per square foot, a live load of 40. We'll say that it's flat. And so the ultimate is going to be 1.2 times the dead load plus 1.6 times the live load. So that gives us a total of 184 pounds per square feet. So there is our area load. And so that's what's going to be occurring in that area on that roof plan. So the span, sorry about the pen again, the span to depth, I'm just going to keep going with that. Span to depth ratio, right, is 10 to 12. So we're going to say that the depth is equal to the span divided by 10, which would be 100 feet divided by 10. So we've got a pretty fairly deep truss here. We're going to be at 10 feet of depth. So from a preliminary design in view from the side here, see if I can get that out. I don't know why this is doing this today. So there is our 10 feet. And so we've got something that goes over about 100 feet. So to keep the 1-to-1, right, the 45 degrees, we're going to end up with 10 nodes right here. So that's going to be a 10-foot panel width. Try and be a little better. That's the panel width, right? And that's to keep this at 45 degrees on the diagonal. A little messy there, sorry about that. So let's take a look at the free body diagram. So I'm going to go back up here. So this is what we're going to highlight. And I'm going to design this one right here. So 100-foot span. We're going to do tributary, right, to its neighbor. This is just a partial plan. So there's our tributary area. So we'd see that we've got 34 feet of tributary width. So this is our free body diagram of our truss. So there's our truss. On it, we would have a distributed load. And so that distributed load is going to equal the area load, which was 184 pounds per square foot, times the tributary width, which would be 34 feet on each side, 17 on each side. That gives us a distributed load of 6.2 kips per lineal foot. And so the moment is going to be WL over 8. Don't know why all those shapes are popping up today. So that's going to be 6.2 kips per lineal foot times 100 feet. That's got to be squared divided by 8. And so that gives us a moment demand of 7750 kip feet. So there's the demand. Now we need to deal with the capacity. So the capacity of the truss, we're going to be able to take the top chord and the bottom chord. So we'd have in compression, all right, there's that load F. Bottom chord would be in tension, also F. Between them would be 10 feet. And so we've got 7. All right, let me see if I can get this calculation here for you. Just having a little bit of stickiness with the technology today. I do not know why. So there is the demand. The capacity is going to be calculated from F times D. And so we know that D is equal to 10 feet. So that would tell us that F would equal 775 kips. So that's what we need to now. We're going to design that top chord in compression for 775 kips. Let's go ahead and take a look. We've got, this is from your workbook, your handbook, hand guide. So we've got W section, and so we've got 10 feet. That's our effective length. So we're going to go over here and look in the 12-foot section, and our demand was 775. So right there, we'll pick 806. That means the capacity is greater than the demand, and so it's going to be a 12 by 72. So this would be a W12 by 72. I have no real idea what's going wrong with the pen today. See if I can get that fixed moving forward. All right, we'll do one more example here if my pen will hold up for it, and see if I can get this to you. So a little cantilever truss. So you see some columns sitting here on the plan. And so on the outside there, both outside, that's the truss out there. So a total of 160 feet, but we've got what we would call a span of 80 feet. That's the cantilevered span. So the S over D, we'll go ahead and use, it could be anywhere from 3 to 4, so we'll use 4. So that would tell us that the depth would have to be 80 feet over 4. So very deep truss here that we're going to need to be able to do this. A huge, huge overhang. Let's get some loads on here. So let's say that this is the second floor, and so the dead load, we'll go ahead and give 80 pounds per square foot. Live load, we'll go ahead and give 100 pounds per square foot. So that would mean that the area load is going to be 80 times 1.6 plus 100 times the 1.2, sorry. That would give us a total load of, so let's go ahead and give ourselves the LRFD load. That's going to be 248 pounds per square foot. Each truss is going to have 30 feet tributary to it. So that would give us a free body diagram that would look something like this. We'd have 80 feet. I don't know why it's doing that. another 80 feet. We would have on it a distributed load. From the first 80, we would have distributed load. Let's go ahead and look at the framing plan again. So over that 80, right, the cantilever would have 30 feet tributary. On the back span, we would have 15 feet tributary. So if you go ahead and do all that calculating, so this would be the 248 times 30. That would give us about 7.44 kips per lineal foot. That would put back here about 3.72 kips per lineal foot. And so from a maximum moment point of view, the maximum moment is going to occur right on top of that roller, whatever, no matter what's going on behind it there. B might be doing that, B might be doing that. The max moment would occur right here. And so we could just take then the statically equivalent point load, which would be 744 kips per lineal foot times 80 feet, that would be the point load, times 40 feet. And that would give us a value for the moment, the max moment in the beam, the demand moment. That would give us a demand moment right there of just under 24,000 kip feet. And so that's the moment that we've got in the truss. And so we're going to take that and divide by 10 feet, or excuse me, the depth, which is 20 feet. We know that the moment is equal to the chord force times the distance between the two chords. So numbers wise, we've got 23,800 is equal to F times 20 feet. That would tell us that the chord force would be just about 1,200 kips. So we'll just keep in mind here that we'll still use the 1-to-1 ratio. So that would mean that the length of that member is also going to be, it's pretty aggressive, it's going to be 20 feet. Sorry about the pen there. I really don't know why it's doing that. I'm pretty tired of that. There's 20 feet. So we'll go back and take a look at the table. And so we've got an effective length, right, of 20 feet. So we'll go in the 21 foot. We'll go down. We're going to find 1,200. And so that would be right about there. We're going to use a 14 by 159 would size our chord.